Imagine trying to learn a brand new language. Okay.
Mm-hmm.
But instead of, translating word by word tediously, sequentially, what if you could just grasp the entire meaning of a sentence instantly? See how every single word relates to every other word, no matter how far apart they are.
Right.
Or just think about the translation tools we use now. They're incredibly fluid, almost. Well, magical in how they get context.
Yeah, they've gotten so much better.
Or even the tech behind those massive, large language models that seem to understand nuance so well.
Mm-hmm.
All these incredible advances, they really point back to the single fundamental shift in how computers process sequences.
Hey everyone, and welcome to The Deep Dive. This is the show where we unpack the most impactful ideas from cutting-edge research. And today we're kicking off something a bit special, a series we're calling Computer Science Tech Papers Summary.
We take one pivotal paper, break it down for you, and really translate that complex research into something compelling, something story-driven. I'm Alex, and I'll be your guide through the big picture, the analogies, maybe some surprising insights.
And I'm Jordan. I'm here to help unpack the technical details, simplify the complex stuff, and really get at the elegant logic behind these, revolutionary ideas. And speaking of fundamental shifts, few papers really embody that more profoundly than the one we're diving into today.
Which one is it?
It's called Attention is All You Need.
That title alone just screams revolution, doesn't it? It sounds audacious, almost like a challenge.
It really does. It was published back in 2017 by a team from Google Brain. I mean, a real who's who.
Mm-hmm.
Sheesh Vaswani, Noam Shazir, Lion Jones. Lots of the names you definitely recognize now.
Yeah.
Giants in the field.
Okay.
And this paper, maybe it's not a household name if you're outside deep learning circles, but it's absolutely a foundational text in modern AI.
Foundational how?
It didn't just, tweak things. It fundamentally reshaped the whole landscape, especially for sequence modeling.
Sequence modeling, like language.
Exactly. Language translation generation. Its ripple effects are still huge today, powering so many things you probably use daily.
Even if the really famous models, the big LLMs, came a bit later.
Right. Even if those came later, this paper provided the essential blueprint. The core idea started here.
Okay, so let's set the stage then. Before this paper dropped in 2017, what was the scene like? What were the reigning champions for dealing with sequences? What was standard practice?
Well, before the transformer, the dominant models for almost anything involving sequences, machine translation, language modeling, even speech recognition, they were complex recurrent neural networks, RNNs.
RNNs, right. I remember those.
And specifically, their more sophisticated cousins, long short-term memory networks, LSTMs, and gated recurrent units, GRUs.
Okay.
Those were considered the absolute state-of-the-art, no question. They'd push things really far, doing stuff that seemed almost impossible just a decade before that.
So they were powerful for their time, the best we had. But, and there's always a but, right? They had some kind of core limitation, something that held them back.
Yes, a really fundamental bottleneck, and that's precisely where the transformer idea comes in.
Okay, unpack that problem for us. What was the big issue with RNNs?
You've hit the crucial point. The core limitation, the really stubborn one, is that RNNs process information sequentially.
Sequentially, like one word after another.
Exactly. Think of it like a scribe meticulously copying a manuscript, one word at a time, strictly left to right. They have to finish processing one word, update their internal memory, their state, based on that word, and only then can they even start looking at the next word.
Right, step by step.
There's an unavoidable step-by-step dependency built right in.
And for us humans, that sounds kind of natural, right? We read that way, we speak that way. So why is that such a problem for a computer, especially when you're training these huge models?
It sounds natural for us, yeah, but for a computer, especially during training, that sequential nature creates a massive bottleneck.
How so?
Because of that dependency, RNNs fundamentally prevent parallel computation within a single training example.
Okay, what does that mean practically?
It means if you feed an RNN a really long sentence, maybe 100 words, the computer has to process word 1, then word 2, then word 3, all the way to word 100 in strict order. It can't just, divide the sentence into chunks and process different parts at the same time.
So it's like a perpetual single file line for information. Doesn't matter how much computing power you have, you're stuck in that line.
Precisely, a single file line.
Yeah.
And that becomes a critical issue, especially for longer sequences. Training becomes incredibly slow.
Yeah.
And super resource intensive.
You can't just speed it up by throwing more processors at one sentence.
Nope. You can't parallelize it within the example. Now, you can batch multiple different examples together, process several sentences side by side,
Right.
but even that is limited by how much memory your hardware has, which again hinders your ability to scale up to really massive data sets or handle very long contexts.
So this sequential constraint was just always there, a constant headache for researchers trying to build bigger, better models.
Well, a constant thorn in the side, yeah. Everyone knew it was a problem.
I seem to recall, though, there were other attempts to break free from this sequential thing, even before the transformer. People tried using convolutional neural networks, CNNs.
That's right. There were models like ByteNet and ConVS2S that tried using CNNs to reduce that step-by-step computation.
Did that work? Were they a real solution?
They were definitely innovative steps, clever ideas, and they did offer some parallelization because CNNs can look at local windows of information simultaneously.
There's a but coming, I can feel it.
But they had their own drawbacks. The main one was that relating distant positions in the sequence still took more work the further apart they were.
Ah, okay. So it wasn't instant.
No. For some CNN models, the number of operations needed grew linearly with distance. For others, it was logarithmic better, but still not direct, not constant time.
So still not that immediate connection you'd want across a whole long sentence, like understanding how the first word relates to the very last word instantly.
Exactly. That limitation made it inherently difficult for those CNN-based models to really nail long-range dependencies.
Long-range dependencies.
Yeah.
Like a pronoun way later in a paragraph referring back to something introduced pages ago.
Precisely that kind of thing. How words at the beginning influence words much, much later. CNNs were better than RNNs at capturing local patterns in parallel, sure, but they still struggle to maintain that clear, efficient connection across really vast distances without needing a lot more computational steps.
Okay. So despite all these efforts, tweaking RNNs, trying CNNs, that fundamental sequential bottleneck just persisted. It was a major hurdle for speed, for scalability, like an invisible ceiling.
It really was. People were optimizing RNNs with clever tricks, adding things like conditional computation, refining the architectures constantly. But that core sequential processing issue remained.
Which must have been frustrating.
Deeply frustrating. There was this huge desire for faster training, for handling longer sequences without memory issues, for actually using all the parallel power in modern GPUs. It was driving this urgent search for a totally new paradigm.
So it wasn't just about making RNNs a little bit better. It was about asking, could we find a truly parallel way to do this? Something completely different.
That was the million-dollar question. Could we ditch the sequential dependence altogether?
Now, let's be clear. Attention mechanisms themselves. They weren't totally brand new with this paper, were they? People had used attention before.
That's a crucial point. Absolutely right. Attention mechanisms had been around, particularly since about 2014, and they were known to be incredibly useful.
What did they do, broadly speaking?
They basically allowed models to focus on the most relevant parts of the input sequence when generating the output sequence, regardless of how far apart those parts were.
So like focusing on the keywords in a sentence you're translating.
Exactly. It let the model dynamically weigh which parts of the input were most important for predicting the next part of the output. It was a powerful tool.
Give us an analogy. How does attention work for us humans?
Okay, think about reading a really dense legal document. You might scan it quickly, but then you focus in, you highlight the specific phrases or clauses that directly answer the question you have.
Right. Ignoring the boilerplate.
Or imagine you're at a loud party, super noisy, but you can somehow tune out all the background chatter and listen intently to just one specific voice across the room.
Ah, the cocktail party effect?
Kind of like that, yeah. That's what attention allowed models to do. Selectively draw connections, weigh the importance of different bits of information, even if they weren't physically next to each other in the sequence.
Yeah.
Dynamic selective focus.
And this is the key part, right? This is what makes attention is all you need. So revolutionary, before this paper, these attention mechanisms were almost always used with an RNN, like an add-on.
Exactly. That's the core revolutionary leap. They weren't the main engine. They were more like a turbocharger or a smart targeting system added to the existing RNN framework.
They improved RNNs but didn't replace them.
Precisely. The breakthrough wasn't just using attention. It was the incredibly bold, almost counterintuitive idea to rely entirely on attention, to completely cut out the recurrent layers, cut out the convolutional layers that had dominated for so long.
That's the all you need part.
That's the all you need part. It basically asked, what if this mechanism we've been using to help RNNs could actually be the entire model?
So the transformer proposal, Ditched recurrence entirely.
Oh.
Rely only on attention to draw connections across the whole sequence. Global dependencies instantly.
Mm-hmm.
That was the paradigm shift, promising massive parallelization, huge speedups. A gamble, really.
A gamble that paid off spectacularly. It replaced that slow sequential tape recorder of RNNs with a highly parallel instant lookup system,
Unlocking speed and scale that nobody could get before.
fundamentally changing how we approach sequences and, yeah, paving the way for models orders of magnitude larger and more capable than anything before.
Okay, let's unpack this thing. We know the problem, we know the big idea. Now, let's get into the nuts and bolts. How does the transformer actually work? What's the core approach?
Okay, so at its heart, the transformer is what's called a sequence transduction model.
Fancy term. What's that mean?
It just means it takes one sequence, like an English sentence, and transforms or transduces it into another sequence, like a German sentence.
Input sequence, output sequence. Got it.
And it uses a very standard structure for this kind of task.
Yeah.
An encoder-decoder architecture. You see this design a lot in translation, summarization, those kinds of tasks.
Encoder-decoder. Can you break that down simply? What does each part do?
Sure. The encoder's job is basically to read the entire input sequence, your English sentence, and kind of digest it,
Yep.
turn it into a rich, abstract representation.
Like summarizing the key information in context.
Exactly. Think of it as capturing the essence, the meaning, into a set of, well, vectors. Then the decoder takes that rich, summarized representation from the encoder
Okay.
and uses it to generate the output sequence, one piece at a time. Like, it looks at the encoder's summary and starts writing the German translation word by word, making sure it makes sense based on the original English meaning.
Got it. Encoder reads and understands. Decoder uses that understanding to write. So what are the actual building blocks inside these encoders and decoders? What makes them tick?
The transformer is built by stacking identical layers on top of each other. For both the encoder and decoder, the paper uses ND6 layers in their base model.
6 layers deep. Okay. What's in each layer?
The encoder stack, each of its 6 identical layers, has 2 main sublayers.
First one.
The first is the star of the show, multi-head self-attention.
Self-attention. That's the core innovation.
That's the core. Conceptually, this lets each part of the input say, each word look at all other parts of the same input sequence.
Look at itself.
Well, look at the entire sequence it's part of. And it dynamically weighs the importance of those other words to understand its own context.
Example.
Okay, the word bank. If it sees bank in a sentence, the self-attention mechanism can immediately look across the whole sentence and see if the word river is nearby, or if the word money is nearby.
To figure out if it's a riverbank or a financial bank.
Exactly. And it does that connection instantly in one shot for all words simultaneously.
Wow. Okay, that's the first sublayer. What's the second one in the encoder?
The second is a position-wise, fully connected feed-forward network.
That sounds more standard.
It is. It's basically a standard neural network, but it's applied independently and identically to each position in the sequence.
So each word gets processed by its own little feed-forward network.
Pretty much. After the self-attention step has figured out the context, this feed-forward network further processes each word's representation individually. It adds more computational depth and nonlinearity, refining the understanding of that word based on its context.
Okay, so encoder, self-attention for context, then feed-forward for refinement, repeated 6 times. What about the decoder? Is it the same?
Very similar structure, also in these 6 layers. Each decoder layer has those same 2 sublayers, the multi-head self-attention and the position-wise feed-forward network. But it has a crucial third sublayer sandwiched in between them.
A third one, what does that do?
That third one is encoder-decoder attention. This is how the decoder pays attention back to the input sentence.
Okay, so while it's generating the translation.
Exactly. As it's generating the German output, say word by word, this layer lets it look back at the final representation produced by the encoder, that rich summary of the English input.
So it can make sure the German word aligns with the meaning of the whole English sentence?
Precisely. It ensures the translation stays faithful to the source.
Makes sense. Now, what about the self-attention within the decoder? Does it also look at the entire decoder output sequence? That seems like it might cause problems if it's still generating.
Good question. That's where masked multi-head self-attention comes in. It's a critical modification.
Masked.
Yes. When the decoder is generating the next word in the sequence, it should only be allowed to attend to the words it has already generated up to that point.
Right. It can't cheat by looking ahead at the answer.
Exactly. It can't see the future words it hasn't predicted yet. So the masking mechanism essentially hides or blocks the connections to subsequent positions. It sets their attention weights to effectively 0 or negative infinity before the softmax.
Clever. So it forces it to be causal, only looking backward in its own generated sequence.
Precisely. This ensures the autoregressive property, predicting the next word based only on the past. It's like writing a story. You can only see the words you've already written when deciding on the next one.
Fascinating. Very careful information flow control. And you mentioned a couple of other standard components earlier, residual connections and layer normalization.
Yes, those are crucial shared elements. They're applied around each of the sublayers, both encoder and decoder.
What do they do again?
Residual connections are like informational shortcuts. They add the input of a sublayer to its output. This really helps information and gradients flow smoothly through deep networks, preventing issues like vanishing gradients where the learning signal gets lost.
Like an express lane for information?
Kind of, yeah. And layer normalization helps stabilize the training process. It normalizes the activations within each layer, which prevents the values from exploding or shrinking wildly, especially in deep networks. Makes training more reliable.
And they kept the dimensions consistent.
Yes, a key design choice was using a consistent dimension, d-model equals 512, for all the layers, the embeddings, everything. This ensures everything fits together nicely, smooth information flow across the whole network. A unified representational space.
Okay, we keep talking about attention as the core magic here. Let's dive deeper into that mechanism itself. How does it actually work fundamentally?
Okay, so the paper describes attention as mapping a query and a set of key value pairs to an output.
Query, key, value. Sounds like a database lookup.
It's a good analogy. Think of it like this. You have a specific question or topic you're interested in. That's your query.
Okay.
Then you have a collection of information sources. Each source has a label or identifier that's its key, and the actual information content is the value.
Got it. Query is my question. Keys are labels. Values are the actual info.
Right. The attention mechanism calculates a score between your query and each key. This score measures how compatible or relevant that key, and thus its associated value, is to your query.
How well does this info source match my question?
Exactly. Then, based on these compatibility scores, it computes weights. Higher scores mean higher weights. The final output is then a weighted sum of all the values.
So I don't just get the single best match, I get a blend.
You get a blend, a weighted average, where the values most relevant to your query contribute more strongly to the final output. It's a soft, dynamic retrieval process.
Okay, and the transformer uses a specific type of attention.
Yes, it uses what they call scaled dot product attention. It's very efficient.
Scaled dot product. How does that work mathematically, in simple terms?
Okay, simplified. First, you compute the dot product between your query vector and all the key vectors. A dot product basically measures similarity, how much two vectors point in the same direction.
So high dot product means query and key are similar.
Right. Then, critically, you divide each of these dot product scores by a scaling factor, specifically the square root of the dimension of the key vectors, score DDK.
The square root of the dimension. Why that specific scaling seems like a small detail.
It's a super important detail. It's a brilliant insight. Here's why. When the dimension decay gets large, meaning your keys and queries are complex, high-dimensional vectors, the dot products can become very large in magnitude.
Okay.
And if you feed these very large numbers into the next step, which is a softmax function...
Softmax turns scores into probabilities, right? Summing to 1.
Exactly. But if the input scores are huge, the softmax output gets pushed to extremes. Probabilities become very close to 0 or 1. Very peaky.
Like it's overly confident.
Overly confident. And crucially, it pushes the softmax into regions where its gradients are tiny.
Gradients are how the network learns.
Yes. Tiny gradients mean learning basically stalls. The network stops updating its weights effectively. It's called gradient saturation.
Ah, so the scaling factor prevents that.
Precisely. Dividing by score, TAT, keeps the dot products in a more reasonable range before they hit the softmax. It keeps the gradients healthy, allows the network to learn effectively. It's like a temperature control for the attention mechanism.
A finely calibrated dimmer switch. Keeps things responsive. Cool.
Very cool. And practically, this dot product attention is also super fast because it can be implemented using highly optimized matrix multiplication routines on GPUs, much faster than some other attention variants like additive attention. Efficiency is key.
Okay, now here's where it gets really interesting for me. Multi-head attention. Instead of just one big attention calculation, they split it up. into multiple heads.
Exactly. This is another core innovation.
Hmm.
The idea is, instead of asking one attention mechanism to figure out all types of relationships in the data simultaneously.
Which might be asking too much.
It might average things out too much. So multi-head attention says, let's have multiple attention mechanisms, multiple heads running in parallel, each focusing on a different aspect or subspace of the information.
How does that work technically?
Instead of using the full D-model dimensional query key and value vectors directly, they first linearly project them down into smaller dimensions, h times independently. H is the number of heads 8 in the base paper.
So you get 8 sets of smaller Q, K, V vectors.
Yeah, you get 8 sets of queries, keys, and values, each with dimensions dk and dv, usually D-model h.
Okay, I have my art critic analogy ready for this one.
Go for it.
Imagine you're analyzing a really complex painting. A single attention head might just look at the overall subject or mood. But with multi-head attention, it's like having a team of specialist critics.
Okay.
One head focuses only on color and light. Another head analyzes just the shapes and composition. A third looks at brushstrokes and texture. A fourth maybe focuses on the historical context or emotional impact.
I like it. Different perspectives.
Yeah. Each head learns a different, specialized aspect of the relationships within the painting, or in our case, the sequence data, giving you a much richer, multifaceted understanding.
That's a perfect analogy. And technically, each of these H heads performs its scale dot product attention calculation completely in parallel, using its own set of projected Q, K, V.
So 8 separate attention calculations happening at the same time?
Mm-hmm. Then the outputs from all 8 heads, these refined value vectors, are simply concatenated, stitched back together.
Making one big vector again.
Right. And then usually there's one final linear projection applied to this combined output to get the final result for that layer.
So the benefit is, it can focus on different things simultaneously.
Yes. It allows the model to jointly attend to information from different representation subspaces at different positions. It overcomes the limitation of a single head trying to average everything. And remarkably, even though you have multiple heads, the total computation is similar to a single head with the full dimension, because you reduce the dimension of each head proportionally.
So for 8 heads, each head works with dimensions 18th the size.
Exactly. In the paper D model is 512, they used 8 heads, so dk and dv for each head were 512, 8 equals 64. It's incredibly clever, adds representational power without blowing up the computational cost.
Mind blown. Okay, so this brings up a huge question. We ditched RNNs, we ditched CNNs. Those gave us a sense of order. If the transformer is just using attention, which seems to look everywhere at once, how does it know the order of the words? First word, second word, last word.
That is an absolutely critical point. You're right, the self-attention mechanism itself is inherently permutation invariant. It treats the input like a bag of words, no built-in sense of sequence.
So dog bites man and man bites dog would look the same to just the attention part.
Potentially yes, without something else. The solution they implemented is called positional encodings.
Positional encoding. Okay, what are they?
They are special vectors that contain information about the position of each token in the sequence. These position vectors are simply added to the input word embeddings at the very bottom of the encoder and decoder stacks.
Added directly to the word's meaning vector.
Yes, so each word's representation gets infused with information about its location in the sequence right from the start.
Are these encodings learned like the word embeddings themselves? Or fixed?
In the paper, they used fixed, predefined positional encodings. They didn't learn them. They used a clever scheme involving sine and cosine waves of different frequencies.
Sine and cosine waves. Why, that sounds specific.
It is specific. Imagine assigning a unique wavy pattern, like a fingerprint or a musical chord, to each position, 0, 1, 2, 3, and so on. Each dimension of the position vector corresponds to a different sine or cosine wave, with wavelengths forming a geometric progression.
So position 5 has a different wave pattern than position 6.
A distinct pattern, yes. The hypothesis was that using these smooth periodic functions would make it easy for the model to learn to attend based on relative positions.
Meaning it could learn pay attention 3 words back or look 5 words ahead.
That was the hope. And crucially, it was hypothesized that this sinusoidal approach might allow the model to extrapolate a sequence lengths longer than any it saw during training.
Because the sine-cosine pattern just keeps going indefinitely.
Exactly. If it was trained on sentences up to 500 words, the pattern provides a meaningful signal even for position 1000, which it never explicitly trained on.
Did they try learned embeddings too?
They did. The paper mentions they experimented with learned positional embeddings and found they produced similar performance results.
Ugh.
But they chose the fixed sinusoidal version specifically for this theoretical advantage of better generalization to longer sequences. It's a subtle but potentially significant choice for robustness.
Okay, so we have this architecture. Pure attention, multi-headed, with positional info added in. Why did this work so incredibly well? What are the big advantages that made it blow everything else out of the water?
The paper really highlights three main advantages compared to RNNs and CNNs. One, computational complexity per layer.
Yeah.
Two, how much can be parallelized. And three, the path length for information flow between distant words.
Okay, let's take those one by one. Computational complexity.
So self-attention scales roughly as ON2D, and a sequence length D is the representation dimension. Recurrent layers are more like OND2.
Which is better?
It depends. Here's the key insight. Self-attention is often faster when the sequence length N is smaller than the dimension D.
Which happens often in practice.
Yes, for typical machine translation tasks using things like word piece or byte pair encodings, the sequence length N, number of tokens, is frequently smaller than the model dimension D, like 512 or 1034. So layer by layer, it can already be more efficient.
Okay, faster for typical sentences. That's good. But you said there was a real game changer.
Parallelization. This is the revolutionary part. This is why transformers could scale like never before.
How parallel is it?
Self-attention layers have O1, sequential operations, constant time.
Meaning
Meaning you can process all parts of the sequence, all words, all attention calculations across all heads simultaneously. In parallel, GPUs love this.
Unlike RNNs.
Exactly. RNNs have ON sequential operations. They must go step by step.
Good.
This O1 versus ON in sequential operations is the fundamental difference that unlocks massive speedups in training. You can finally leverage modern parallel hardware fully. Training times went from weeks or months down to days or hours.
That's huge. Okay, advantage 3, path length. This relates to that long-range dependency problem we talked about.
Precisely. Learning how words far apart influence each other is crucial, especially for language. The shorter the path signals have to travel through the network, both forward for prediction and backward for learning gradients, the easier it is for the model to learn these connections.
So shorter paths are better. How does self-attention compare?
For self-attention, the path length between any two positions in the sequence is O1, constant.
Constant, meaning instant connection.
Effectively, yes. Any word can directly look at and influence any other word in a single computational step through one attention hop. It's like a direct lines of communication between everyone in a stadium.
Wow. And RNNs?
RNNs or ON. The path length grows linearly with distance. Information has to pass sequentially through all intermediate steps.
Making it harder and harder to remember things far back.
Much harder. Signal degradation, vanishing gradients. Even CNNs, which were better, had path lengths like O or OLOG. Still growing.
So this O1 path length in self-attention is the aha moment. It fundamentally makes learning long-range dependencies much, much easier. It cracks that problem.
It completely changes the game for understanding context across long distances. It removes that bottleneck.
Incredible. And the paper mentioned another benefit, kind of a side effect, but really cool, interpretability. We can actually see what it's doing.
Yes. This is one of the really fascinating aspects. By visualizing the attention weights, seeing which words are paying attention to which other words, they found something amazing.
What did they find?
Individual attention heads actually learned to perform different interpretable tasks. They weren't just random weights. Many heads showed clear patterns related to the syntax and semantics of the language.
Like they specialized.
Exactly. It's like getting a peek inside the model's thought process.
Can you give an example? What kind of tasks did heads learn?
Sure. The paper has great figures showing this. For instance, they found specific heads in the encoder, layer 5, I think, that seemed specialized in handling syntactic dependencies or completing phrases.
Completing phrases? How?
In the sentence, making the registration or voting process more difficult, one head strongly attended from the word making directly to more difficult, effectively linking those parts of the verb phrase even though they're separated.
Like it recognized the pattern making difficult.
Seems like it. Another really cool example was anaphora resolution.
Linking pronouns to what they refer to, that's hard.
Super hard. But in the sentence, the law will never be perfect, but its application should be just, they showed an attention head where the pronoun its was strongly attending back to law.
So it correctly figured out what it's referred to.
Explicitly, yes.
Yeah.
You could see the connection being made by that head, This kind of observable behavior, these windows into the model's internal reasoning, make it feel less like a complete black box.
Yeah.
It's a huge win for understanding how these models work, not just that they work.
That is really cool. Not just better performance, but maybe a path towards more transparent AI. Okay, so this wasn't just theory. It actually worked. Tell us about the results, the breakthroughs, particularly in machine translation.
The results were, frankly, stunning at the time. On the standard WMT 2014 English to German translation benchmark, their big transformer model achieved a BLEU score of 28.4.
BLEU score. Higher is better. Measures closeness to human translation.
Right. And 28.4 might not sound huge in isolation, but it blew away the previous state of the art. It was over 2 full BLEU points better than the best previous models, including ensembles.
Ensembles meaning combining multiple models.
Yes. Beating even combined models by that much was, well, kind of unheard of. A 2 BLEU point jump on a major benchmark like WMT was a massive leap.
A mic drop moment, like you said.
Pretty much. And get this, even their smaller base transformer model, trained with less compute, by itself outperformed all previous single models and even some ensembles. And it did it at a fraction of the training cost.
Wow, so even the cheaper version was state-of-the-art. What about other language pairs, like English to French?
Similar story. On WMT 2014 English to French, their big model hit 41.8 BLEU, another new single model state-of-the-art.
And the training time was key, right?
Absolutely crucial. They reported training this big model in just 3.5 days on 8 NVIDIA P100 GPUs.
Which just sounds like a lot, but compared to
the weeks or even months it took to train previous top models on similar hardware, it was, as they put it, a small fraction of the training costs.
And that efficiency is maybe the biggest deal. Faster research, more accessible.
It's an enormous deal. They showed the computational cost in FLOP's floating point operations. The big transformer needed about 8 times fewer FLOPs than the previous best ensemble, GNMT plus RL, for English to German, while getting a better result.
8 times less compute for a better score. Okay, that changes everything.
It really does. Faster iteration, bigger experiments become possible, research accelerates. It democratized large-scale model training to some extent.
So it crushed translation, but was it just a one-trick pony? Did it work on other types of tasks?
They tested that specifically. They applied it to English constituency parsing.
Parsing, figuring out the grammatical structure of a sentence. Noun phrases, verb phrases, etc.
Exactly. It's a different kind of challenge. Very structured output, needs deep syntactic understanding. Output can be much longer than the input.
And how did the transformer do there?
Really well. Even with limited training data, not just the Wall Street Journal, part of the Penn Tree Bank, about 40K sentences, it outperforms strong established parsers like the Berkeley parser.
On its own?
Yes. And then, when they used semi-supervised learning pre-training on a huge data set of unlabeled sentences before fine-tuning on the posting data, it achieved an F1 score of 92.7.
Which was
better than almost all previously reported models at the time. It really showed the architecture was robust, general purpose. It wasn't just for sequence to sequence. It could handle complex linguistic structure analysis, too.
Okay, so revolutionary results, incredible efficiency. But no paper is perfect, right?
No.
The authors themselves acknowledged limitations. What were some of the constraints or challenges they pointed out?
Right. They were very upfront about it. One key limitation stems directly from that ON2D complexity of self-attention. While it's great for typical sentences, it can become computationally very expensive for extremely long sequences.
Because N2 grows really fast.
Very fast. If n is the number of words or tokens, doubling the length quadruples the computation in that attention layer.
So feeding it an entire book, like hundreds of thousands of words, that would be a problem.
A huge problem for the standard transformer. It would likely run out of memory or take an extremely long time. N2 just becomes prohibitively large.
Did they suggest any solutions?
They did, even in the original paper. They mentioned the idea of using restricted self-attention as future work.
Restricted how?
Instead of every word attending to every other word, each word would only attend to a smaller local window or neighborhood around it, say size R.
Limiting the scope.
Exactly. This would reduce the complexity down to ORND, which scales linearly with sequence length n, much better for very long sequences. The trade-off is that the path length increases slightly to ONR, meaning you need more steps to connect very distant words.
So a trade-off between computation and direct long-range connection. Smart thinking ahead.
Definitely. They knew the N2 was a potential bottleneck for extreme scales.
What about other design choices? Did they find things like the number of heads or that decay dimension really mattered? You said it's like tuning an engine?
Absolutely. They did ablation studies, basically removing or changing one component at a time to see its effect. They found the number of attention heads was important.
More isn't always better.
Right. They found that using only a single head hurt performance significantly compared to 8 heads. But they also noted that too many heads could potentially be detrimental too, maybe because each head gets too little capacity. Finding that sweet spot, 8 in their case, was key. And that key dimension, decay. They tried reducing it and found it negatively impacted model quality.
Meaning?
It suggests that figuring out the compatibility between queries and keys is actually a complex job that benefits from having a reasonably high dimension, 64 per head in their case. It implies that simple dot products might need that richness to capture subtle relationships effectively.
Interesting. Raises questions about whether dot product is always the best way to measure compatibility.
Exactly. Could more complex functions do better? It's an ongoing research area.
What about training stability? Did they need tricks like dropout?
Yes. They mentioned dropout was very helpful in avoiding overfitting, which is standard for these huge models. They applied it after each sublayer and to the embeddings plus positional encodings.
And label smoothing?
They use that too. It slightly discourages the model from being too confident in its predictions, hurts perplexity a tiny bit, but usually improves overall accuracy and BLEU scores. Just another small tweak for robustness.
And back to the positional encodings, sticking with sinusoidal, even though learned ones work similarly, that was purely for the extrapolation idea.
That seems to be the main justification given. The potential for the fixed sinusoidal pattern to generalize better to sequence lengths the model had never seen during training. Even if learned embeddings worked fine on the test set, the sinusoidal ones offered this theoretical robustness against unseen lengths. A subtle but forward-thinking choice for a foundational model.
Okay, so the paper ends. Authors are excited. Looking back now from, today, that excitement seems incredibly justified. Where did they see this going back in 2017? What future directions did they map out?
They definitely had a grand vision. A major direction was applying the transformer beyond just text.
To other types of data.
Exactly. Problems involving other modalities, images, audio, even video. They clearly saw attention as a general mechanism, not just for language.
So the idea that attention could unify AI tasks, seeing relationships in pixels, sound waves, not just words.
That was definitely the implication. That the core concept, dynamically weighing relationships, could work across diverse data types.
And they were already thinking about how to handle the scale needed for images or long audio.
Yes. They explicitly mentioned investigating those local restricted attention mechanisms to efficiently handle the massive inputs and outputs you get with images or audio, directly addressing the N2 scaling challenge for those domains.
And what about making generation less sequential? The decoder still generates word by word, right?
Right. The decoder is autoregressive. It predicts token T based on tokens 1 to T1. They envisioned future work exploring ways to parallelize the generation process itself.
Like generating a whole sentence or paragraph at once.
Or at least larger chunks simultaneously.
Right.
That would drastically speed up inference time. How fast the model produces results in real applications. That's still an active research area today.
And crucially, for the whole field, they released their code.
Yes, absolutely. They made the code available via TensorFlow, Tensor2, Tensor.
Yeah.
Huge for open science.
Why is that so important?
It allows for reproducibility, others can verify the results, but more importantly, it accelerates research massively. People could immediately build upon their work, experiment, adapt it, without starting from scratch. It was a key factor in how quickly the transformer architecture spread and evolved.
Okay, let's step into the speculative corner. It's 2017 then, now we're here, connecting the dots. That constant path length, the parallelization, the efficiency. How did this paper really set the stage for the AI landscape we see today, even if they didn't explicitly say we're building GPT-4?
Oh, the groundwork is undeniable. Those core transformer ideas, the ability to capture global dependencies instantly via O1 paths, the massive parallelization enabling training on huge data sets, the resulting efficiency gains, they are the absolute bedrock of today's large language models.
So things like GPT, LaMDA, Claude, they're essentially descendants.
Direct descendants, massively scaled up. The ability to train models with not just millions, but billions or even trillions of parameters on internet-scale text data. That became feasible because the transformer architecture was so parallelizable and efficient.
You couldn't have done that with RNNs.
Simply impossible. Imagine training a trillion-parameter model where every calculation for a long sequence had to happen step by step sequentially. It would take, well, effectively forever.
So attention is all you need really did become kind of a self-fulfilling prophecy.
In many ways, yes. That combination of seeing long-range context easily path and being able to train efficiently at unprecedented scale unlocked emerging capabilities we hadn't seen before. The original paper's insights are directly responsible for the era of large-scale general-purpose AI we're in now. Without it, the path would have been vastly different, much slower.
Truly foundational. A single idea sparking a revolution.
A classic example of disruptive innovation in computer science. It really changed everything. Okay, so the TLDR, for attention is all you need. This paper introduced the transformer, a model that ditched recurrence and convolutions entirely. It relied solely on self-attention to understand relationships across sequences. Big advantages. Massive parallelization, leading to way faster training of bigger models. Constant path length for easily learning long-range dependencies. It smashed state-of-the-art results in machine translation and showed it could generalize to other tasks like parsing. Its multi-head attention let it focus on different things at once, and positional encodings gave it order. Basically, it rewrote the rules for sequence modeling and directly enabled the large-scale AI we see everywhere today.
So what does this all mean for you listening right now? Well, next time you use a translation app or you talk to a smart assistant and it just gets your complicated sentence, the context, the nuance, take a second. Consider that under the hood, it might just be an attention machine doing its thing. Seeing the whole picture, the whole tapestry of information pretty much instantly, not just step by step. And it makes you wonder, right? What else can attention revolutionize? What other hidden connections are waiting out there in huge data sets? Connections that this approach might finally let us see. That's all the time we have for this deep dive into Attention is All You Need. Thanks for joining us on the Deep Dive Computer Science Tech Paper Summary. We'll be back soon with another fascinating paper.
Until then, keep asking questions, keep exploring.